Thank you. And if you're just joining us, welcome to Circuit Insults. All right. It's okay to laugh, you know. This is Circuit Insults. All right. Tough crowd. And I have a slide advancer here as part of the package.
It's all in one.
All in one. All right. Okay. Data converter, the term is actually kind of antiquated. It comes from a simpler time when there was a whole lot less data and very few options for converting it. But what it refers to here is circuits that convert from the analog domain into the digital domain and back again. So that is the analog to digital conversion and digital to analog conversion. The field of data converters is huge. And we can't talk about anything. There's probably thousands of different architectures and hybrids of different architectures that you could look at. But we're just going to do a brief tour and hit the high points that will give you an idea of how the field is organized. So if we have time, we will be dealing with, first of all, DACs, digital to analog converters, or D/A, D to A, and then A to Ds, or ADCs, analog to digital. And if we have time, then we'll go into two particular architectures that are good for high speed. So let's proceed. But first, how many of you know this movie? Oh, phew. Okay, good, good. You see, I discovered that it was actually released probably before you were born. So I thought maybe you wouldn't know about it. But this is, in this movie, the pretext is that we live in a world that is a digitally synthesized illusion. Okay, we're part of a simulation. What we think of as reality is part of a simulation. And that's not reality. In reality, we're all much more cool and we wear sunglasses. Okay, so, but the thing about this, and the reason it made its way into the title, is that this idea of living in a digital reality is much closer to the truth than we care to admit. You know, everything we interact with, you know, everything that interacts with us is now part of a digital system in one way or another. And the reason for this is that the signals that measure the real world and the signals that we interact with are all analog. So, you know, any information that goes into the digital system, the matrix, okay, has to come from the analog side, and it has to go through an A to D, go here through an A to D converter. Likewise, if any digital system wants to influence the real world, then it has to go through a D to A. You know, so this side is all sensors, you know, imagers, microphones, anything like that. And then the other side is all things that we would affect our senses, like displays, speakers, so forth. All has to go. So everything goes in and out of the digital reality by means of converters, data converters. So this is a picture here of the overall converter application space, and this hits many of the highlights, but it's vast. I mean, it covers an enormous amount of material. Up in the upper left, you know, you have things like radar, where you need to take a sample. The signal's moving very fast, so you have to take a sample and take a measurement every nanosecond or something like that, right? And but it doesn't have to be very accurate, okay? So maybe 10 bits worth of resolution is all you need. On the other extreme, you have something like audio, okay, which is you need to take a sample maybe every 10 microseconds or something, and that takes a lot more resolution. So you got the whole spectrum here of, you know, trade-off between speed and resolution in the converters, but it's covering the entire kind of signal space. And so up here, you know, this line here shows where you see published works in the big conferences and so forth. Those are where those papers are going to be. My career has been at the other extreme, down to the low performance area. I've been pushing that envelope. All right. All the things that were on that previous sheet were kind of the high performance end, okay, the things that really determine the end product performance. But in fact, there's a lot of converter use that's behind the scenes that isn't very glamorous, but it's still very important. And this is kind of an old slide. Nobody uses standalone digital still cameras anymore, but it gives you an idea of all the functions that need a converter, okay? And the only one in this list, pushing the wrong button again, the only one in this list that doesn't is just this data compression, which is just a purely digital function. But all these other things, the lens drivers, the stabilization, the display drivers, the touchscreen, all those things require converters, all right? And beyond that, within even big digital chips, a lot of the control and supervisory functions have to use converters to monitor things. You know, what's the on-chip voltage, or setting the on-chip voltage, monitoring the temperature of the die, adjusting the data timing, adjusting the output signal levels, various things. All these are inside what is basically a digital chip, okay? But it has all these converters to monitor and supervise analog signals. Okay, so that's why everybody needs converters. But what is really a bit of a mystery is why converters are so popular, all right? I've had colleagues come to me and say, well, how can I break into this converter business? I want to, I'm doing this or I'm doing that, and I'd like to get into converters, that looks like it's really great, And I have had people in job interviews who would say, well, I only want to work in converters, don't offer me any other job. I would turn it down. I want to work in converters. Everybody's excited about converters. My first job, okay, I was assigned to work on op amps, right? And it was a big opportunity. I mean, we had a new process. It was perfect. This was a career-building opportunity, right? And I said, no, wait, I'll get to that. I have this idea for an A-to-D first, and I would focus on that, and eventually they gave the op amp assignment to somebody else who instantly became a fellow. But that was the point. I was so addicted to this converter work that I just couldn't stop. Okay, so it's a bit of a mystery. I think there are several reasons why it's so popular. One is, of course, it's important. I mean, everything relies on these converters, okay? And it's constantly moving, virtually inexhaustible demand for performance. But I think the biggest thing for me is the creativity that goes into some of these designs. Now, all design work in IC business, there's lots of creativity, and it's not really that different, but for some reason, there's just a lot of options in this converter that make it nice, and I think fundamentally, all forms of engineering are quite similar, in terms of the thoughts and the satisfactions that you have from doing that kind of work and so forth. But, if you're building a bridge, you can't be too creative, right? You can't say, well, let's try this, or maybe let's try this other material. How about recycled cardboard? You don't have that option, right? You have to kind of make sure that bridge stays up forever, right? But with electronics and doing things like these converter systems, or really any kind of IC, you have that option, and you can say, well, what if we rethink this and do it another way? So it's the creativity, the brainstorming, the breakthroughs that make it really interesting. And of course, it's hard. It's challenging, and it's also very visible in your organization. And if you do a good job with the converters, people will notice. Okay. So the first thing we're going to attack here is the digital to analog converter end, okay? And there's a reason we're doing this first, and that should be apparent later. But the fundamental element in a D to A converter, a DAC, is really just a switch, right? And because the object of a DAC is to make a voltage or current under digital control, right? So you have a switch that goes between VREF and ground, okay, and that is basically just a DAC, okay? So, you could imagine that this switch might be a MOS transistor or something like that, so. So the simplest form, I think, the place to start is with this thing called a string DAC, okay? And here, you can see on the left-hand side, you put some sort of reference voltage here, and it goes through this divider, and all these different intermediate voltages are created, and then under digital control, you switch in one of them and switch it to the output. Okay, so that's basically a DAC, right? You select which of all those voltages you want. And this has been around for a long time. This is Lord Kelvin. Okay, he's the guy from the Kelvin temperature scale, also Stokes' theorem and countless other things. And he apparently worked as Santa Claus in the department store at Christmas time. He was one of the first people to do this. And in fact, he invented another part of this, which is called the segmented DAC. All right, now here, on the left, you can see that you don't want to divide too many, you don't want to have too many taps on that resistor divider. It's basically, you don't want to have, so how many bits can you really do with just that resistor divider? You can't do very many, right? I mean, you might do 10 or so for 10 bits, but beyond that, you couldn't do it, okay? Just because it would get out of hand. Every time you increase the number of bits, you'd have to double the number of taps, right? So it gets out of hand in a hurry. Well, one of the ways to get around that is this is called a Kelvin-Varley thing, and it's to take two of those taps and then interpolate between them with another DAC. Okay, so it's kind of a two-stage DAC, if you will. It's kind of a coarse and a fine DAC. And this technique is used for mostly in things like setting voltages for process control or AATE. Here's an example. Whoops. Here's an example, and I've taken a lot of this stuff from my former employer. They're not the only game in town, but I was pretty sure they wouldn't sue me for using their copyrighted material. So this is a chip. It has 40 of these string DACs that are 16 bits good, okay? So it's an enormous amount of resolution, and it is widely popular in places where you have to set a lot of voltage, like automated test equipment, optical communications, industrial control, and instrumentation boxes. So that's popular use for that. Now, at this point, I want to introduce one of the fundamental principles, which is there must be a reference involved. And this, here's another movie reference, Spinal Tap. This guy is very proud, this musician is very proud of his amplifiers that go to 11, whereas most amplifiers, you turn them up all the way, it's a 10, right? His amplifiers are 11, okay, and he's very proud of this. Okay, the joke is, of course, that it's 10 or 11 what? It has no meaning without a unit attached to it, okay? And that's the same thing with the DAC. The DAC must have a reference to tell you, each LSB is worth how much voltage or how much current, right? So there has to be that reference in there. It may not be a very good reference. I mean, maybe you use a power supply, but there's something that's determining that. So that's one of the fundamental things that you need to look for in each of these designs. Okay, the next kind of DAC that we want to look at is called a binary weighted kind of DAC. And this slide here is not the DAC itself, but it's the principle on which the DAC operates. It's a kind of a switch capacitor circuit, and quite possibly many of you are already familiar with it. You see on the left, what we've got is a circuit, an op-amp circuit, where we've zeroed out all of the capacitors. We've shorted them all out, and so there's no charge on any capacitor. All right, but then we take a 1-volt source and put it right here underneath the 2C capacitor right here. And so that 1 volt lifts up that capacitor to 1 volt, and now you've got that places 1 volt across the input of the op amp here. And okay, so the op amp goes wildly negative and drives the output down until it can pull this input node back down to ground. Okay, and when it does that, you pull this up, so all the charge has to be removed from this cap here. But this cap on top is half as big. So you move all that charge onto a capacitor that's half as big, you get an output that's 2 volts, right? Not 1 volt, okay? So you get a kind of multiplying effect, but it's weighted by the size of the capacitors. All right, so here's the actual DAC, all right? So you have a collection of different size capacitors. They are binarily weighted, right? And they are feeding into this little feedback circuit here. And by switching one between ground or the reference, you can create a voltage of a weight that's proportional to that bit. So each bit of your 3-bit, this is 3 bits here, each bit goes directly to one of the switches, okay? So your LSB, your least significant bit, would be attached to the 1C, and then the MSB would be attached to the 4C, and so the DAC would normally work automatically. So this doesn't require any special digital conditioning of the drive signal. These are just the bits of your control word. Okay? Now, you have to periodically reset this, to get all the stray charge away from there. So this is the reset phase. Everything gets grounded, the input capacitors and the feedback capacitors, and that's all important for the operation of this. So it has 2 phases. One is a reset, and then you put in the data and you get an output. So during reset, you get 0. So that's not great. And because of this, you don't see this DAC much in as a standalone product. These kind of DACs here are most often used as signal processing elements. Okay, within a larger system, it's a subsystem where you're doing like switched capacitor analog processing, and we'll see a couple of examples where this is used later on. But you don't see this as a standalone product very often, so I don't have an example for that. But if instead of capacitors you use resistors, DACs like this used to rule the world. Okay, all DACs were like this with resistors in them. Audio DACs, everybody in the old days. Not so much anymore. Okay, here's another DAC, another way to do the DAC. And in this case, imagine you take a bunch of current sources. Okay, they're all the same value. All of them are equal, all right? And then depending on your input code, you switch in a number of these, and the more you switch in, the bigger your output, okay? And so this is very simple. In fact, the circuits for it are extremely simple. Here, it looks something like that. In reality, they are much more complicated than this. There's a number of reasons why they need to be more complicated than this, but fundamentally, this is what's happening. The current source itself is this transistor down here. It's got a fixed voltage. It creates a current, and then these 2 transistors decide which way the current is switched. Whichever one is higher has a higher gate voltage, takes the current. Okay, so this is how you'd make one of those. You add some doodads onto that to make it more practical. But these kind of DACs are the fastest DACs that are available. Here's one. This product here has 4 DACs. Each one is 16 bits at 12 gigasamples per second, okay? And so these DACs are very popular for communications applications, particularly in like the base stations for cell phone towers. The main transmitter that goes into cell phone towers is a very high performance radio, and that's used to generate the signals that are going into the antenna of that base station. And direct RF, phased array, direct digital synthesis. You know, it's like an arbitrary waveform generator or something like that, you can do that. These are very high-speed DACs. All right. Now, there's one more DAC principle that I want to introduce, and that is the idea of sigma delta. And here, you know, instead of representing a signal as a simple voltage or a current, you're using a signal which has only, in this case, only two values, you know, high and low. But the duty cycle of this signal represents the quantity you're trying to transmit. So you're switching the output back and forth very rapidly. But this signal may spend more time at the high level and less time at the low level, makes for a higher signal or a lower signal. Basically what you do is you're going to filter this signal, and when you do it, you filter it enough, you're going to get this kind of sine wave thing here. And so this is very useful for, it's a very simple driver, obviously, because you only have two voltages. But it's good for situations where you have a continuous signal and basically a low frequency load. For example, this is very popular for things like audio. You wouldn't think it would be, right? I mean, because this is the ugliest signal imaginable, but you're putting it through basically a low-pass load, which is a filter. The speaker itself has kind of filter properties, and you add some additional filtering with that too. But anyway, it takes this signal and then turns it into a beautiful analog signal, and that's definitely the way to go. Now, to make this is a very intriguing concept. It uses this loop that we have here, and this loop can be either analog or digital form. But for the DAC, it's mostly digital. So you know you have a digital input here. This is actually several bits maybe, and then you have the output, which is a single bit, but it's switching very fast, and so it goes around, and the switching signal is subtracted from the input. You promised me this was working. Is compared to the input and then integrated, basically filtered, right? And so that really ugly signal we were looking at before gets filtered, integrated, and then the comparator says, are we too high or are we too low? And if you're high, then you switch it low, right? And if you're low, you switch it high, right? So, and the object is this loop is trying to keep up and is trying to balance this switching signal against the input quantity, okay? Which is, that side of the loop is actually digital, but you're getting this one bit output that's switching back and forth. And this is a very powerful concept, and there's actually a lot of embellishment, a whole lot of technology that goes into this. Elaborate filtering, it's an amazing concept. But this is the basic idea. And of course, the DAC in this case, if you just use this one bit and then you drive that switch that we saw in the beginning, then you see that gives you what you want. And this is widely used. This is an audio product that's 12 DACs, 24 bits at 192 kilosamples per second, and it's all about digital audio. So surprisingly, for such a performance-oriented domain, where you want really clean signals for your audio environment, they use such an ugly-looking signal, but it works. Okay, so just to kind of summarize the DAC world, we talked about 4 different kinds of DACs: the string, the binary weighted, the fully. I don't know if I actually labeled that for you, but this is often called fully decoded DAC, and the sigma delta. And each of these 4 has some properties that we're going to see again when we look at the A to D space. The reverse, the converse of that. So this in the string DAC up at the top is basically it's making every output in advance. You know, you're gonna have a DAC with all these different outputs. They're all made in advance. You select which one you want with a switch. The slightly more efficient version is this binary weighted thing where you add in a current or a voltage that's binarily weighted so that you can drive that system directly. And then down here, we have unit weighted, okay, where each of the things that you switch in are of the same value. And finally, in the sigma delta case, it's really time weighted. It's the duty cycle which carries the information. Okay, so those are the four general principles, and we'll see that again as we go into the A to D space. Okay, so now we're going to talk about analog to digital conversion. What we did before was, you know, digital driving an analog signal out to drive a motor or a speaker or whatever. Okay, now we're talking about a circuit which takes an analog signal and converts it, encodes it into digital. Okay, now, if you think about it for a minute, how would you do this? You know, it's not, if you're just starting from scratch, you know, you're inventing electronics, how would you do this? I mean, this is not an obvious thing to me. But let me see if I can make it plausible. The fundamental element here in the A to D conversion space, like in the DAC case, the fundamental thing was a switch, right? You're going to select something. In the A to D space, the fundamental thing is the comparator, which takes two signals and says, which one is bigger? Okay, it's making a comparison, it's making a measurement, all right? And the way you do that is with basically with a latch, okay? And that's what I have here on the left is a latch, you know, that can take one of two states, right? But it will, if you were to take an analog signal and put it there and one there and then let go to see which way it flipped or it flopped, that would be basically what a comparator does. Let me make that a little bit more specific. Okay, so here is the schematic for basically this circuit, right? You get two inverters in a loop, right? And so this circuit is going to balance its positive feedback. You let it go, it's going to snap one way or the other, okay? But it's not going to stay in the middle for very long. And when you get right down to it, this is what the details of that circuit are going to be. This is called the strong arm latch, and this is very popular in analog use. Now, there's lots of different forms of this. You know, it's a latch. It's called a sense amp in memory chips, or a comparator in general analog work. But here you can see in the center is that cross-coupled the loop of inverters right here. And the rest of this stuff, you know, these switches over here and these over here short out everything and remove the previous answer. And then you put the input signal goes in down at the bottom. Okay, and that looks like our DAC switch. But these two voltages, VN1 and VN2, are very close to each other, for example, and you turn the thing on and you let go of those switches that are all labeled S, and the regeneration, the positive feedback starts, and that latch snaps into one state or another. So that's what the circuit looks like in a practical way. Okay, but this is the fundamental component of all A to Ds. This is making a decision. Okay, now the simplest way to use that, I think, conceptually, is like this. And then we can see on the left is our old pal, the string DAC. Okay, and this is called a flash converter. And I think it's called this flash converter because it's very, very fast. I don't know, the British have a different meaning for flash, but it's very, very fast. It is probably the fastest thing you can do, because basically what you've got here is you've got all the voltage levels that you want to measure, right? And then you've got one comparator just waiting, you know, to compare the input to its reference level. So all those comparators are waiting, and then you clock the thing, and they all decide, and you say, oh, okay, this one's 1, that's 0, that's 0. Okay, I know what the voltage is. right? Because it's comparing this input voltage here to all of those reference voltages on the left. Okay, so this is very, very fast component. Now, this illustrates the second kind of fundamental principle that I wanted to introduce here, and that is that basically every measurement is a comparison, okay? You're comparing the input signal to something else, and that something else, you know, I've kind of obscured this picture with there's like little weights that you have to put in the pan and balance out and find out what that unknown quantity is in the left. That's basically a DAC, okay? You're taking the DAC and you're comparing the input signal to the voltage or current on the DAC, okay? And this is a way you can tell what that voltage is. So, every measurement is basically a comparison, and what you compare it to is a DAC. So every ADC must have a DAC embedded in it somehow. Okay, sometimes it's a little hard to figure out what it is, but basically that's what it is. You know, you've got comparators comparing your analog input signal to various outputs of a DAC to find the right one. And it's important to know this because generally you can't do better. The performance of your ADD will not be better than the performance of your DAC, right? I mean, it's like the measurements you make depend on how accurate your ruler is, right? So the DAC is very important. So it's kind of a hierarchy, and that's why we talked about the DACs first, okay? Because there's a dependency here. And every ADC must have at least one comparator because you're making decisions. Okay, so one of the most famous and popular forms of ADC is called the SAR, which stands for Successive Approximation Register, which was a little bit of digital logic, very simple logic that was a big deal back when this was invented. Okay, but what you have is on the left here, you have the analog signal coming in, and it goes this thing called the track and hold, which isn't essential to the concept, but what it does is it holds the input here still. Okay, so it doesn't change while you're doing this conversion operation, while you're measuring the signal. And how this works is the DAC here is going to be adjusted and adjusted and adjusted until the comparator changes state, all right? So you can compare the input to different DAC voltages. Now, the way we're going to do this is we're going to do what's called a binary search, all right? Which means that we're going to the first test we're going to do on the input signal is we're going to say, is it above mid-scale or below mid-scale? The one half there is one half of the reference, okay? So that'd be mid-scale of the entire range of the converter. So is it greater than a half or less than a half? Okay, so if it's greater than a half, yes here, then we want to know if it's greater than 3/4, all right? So now imagine that the DAC you're using is one of these binary weighted things, right? So to do this first test here, you turn on the MSB, okay? And the value of that is half of the digital word. So you get half of the reference, right? So if it's greater than that, now the next thing you want to know is it greater than 3/4? Well, the way to do that is to leave the MSB on and then turn on the next bit. Okay, so the next MSB, that gives you a value in the DAC of 3/4, right? And you go down the DAC one bit at a time, testing it against the input, right? Now, I want to compare that to Albert's presentation where he used a single slope ADC, and that's a specialized kind of converter that's perfect for the application that he has, but this is a linear search. In other words, you go up, you know, is it 1, 2, 3, 4, 5? This binary search is kind of more efficient in time because you say, okay, how many steps do I have to go? And you know exactly how many because it's the number of bits. Whereas the linear search, you're never quite sure how many it's going to take. It may take you every LSB. Okay, so here's our old friend, the binary weighted DAC. Okay, now what we're going to do is we're going to test each of these bits, okay, against the input, and that's going to look if you look at the voltages involved, it's going to look something like this. Okay, so here, over here on the left, this is in time here. Over here on the left, you're going to compare it to 1/2. Okay, and in this case, the input, which is this line, this horizontal line, says V in. That bit is too big. Okay, it's much greater than the input, so we turn that one off. Okay, then we check the next MSB, okay, which is here. We turn that one on, and that one's too low, all right? So we leave that one on, okay? Then we check the third one, the third MSB, and that total, these two bits, the second and the third one, are too much. So you turn the third one off, okay? And then you try the fourth one. Okay, so you can see that the line is getting progressively, successively closer to the input level. You know, you're servoing the DAC to make it close to the input level, and then the value that you have on the DAC is the output code. And this is all very wonderful because it works very well with this binary weighted switch capacitor DAC that we were looking at before. Okay, and one of the reasons it works so well is that you can also do kind of the sampling function and the subtraction function by this arrangement here. So instead of zeroing out all the capacitors in this DAC, instead of doing that, what you do is you put the input voltage on all the capacitors here. And see, at that time, you short this switch to ground, and so all the capacitors will have the input voltage across them. So you're starting from that point. And then you go ahead and start switching in the reference. You have to open this switch here, of course. And then you start comparing it to the reference one bit at a time. And the comparator is just looking at this node here, the summing node, and it's trying to pull, the DAC is trying to pull this node back down to ground, okay, and by checking one bit at a time, and if it goes below ground, whether you keep the bit or you don't keep the bit depends on the sign of what the comparator is doing. So it's a very nice fit, because right in this structure we have the DAC function, obviously, but we also have the kind of sampling of the input, and we have the subtraction that subtracts the DAC value from the input. So it's very clever. And these are probably these days most widely used kind of ADC. They're everywhere. This particular one does 24 bits at 2 megasamples per second for precision measurement. But there are lots of things that don't require that level of performance, and so the SAR is very, very popular these days. But these things go in cycles. When I started working, the SAR was kind of a museum piece. It wasn't. Nobody was doing any research on it. It was kind of forgotten. But the truth is that this architecture is very very well suited to the modern process, low voltage, small transistors, because there's very little circuitry here. You have switches and you have a comparator. You don't have any op amps, you don't have any strange buffers, you don't have any of that stuff. It's well suited and scales well with future processes. So it's become I would say the primary form of ADCs in use. Okay, skip that. Again, it's very simple. It's good for low supplies, and it is perfect for SoC systems on a chip. Okay, so you'll see it in a lot of papers. Okay, here's the sigma delta version. Remember we saw the sigma delta DAC, which had this 1-bit output. Okay, so now we're going to measure, instead of putting in a digital word, the input that's over here, the signal here is an analog signal. And then we have the switch DAC here, the 1-bit DAC, is compared to that. But the principle is the same. The loop is going to try and balance the average of the output and the signal. The difference between the signal and the feedback is going to be driven towards 0, right? And so the duty cycle of your 1-bit DAC, which is coming out there, is going to be the right value. Now, this is only a 1-bit output, right? And this is an A to D, right? So you've got to take this duty cycle and figure out what the value really is. So this is done with a sequence of kind of different filters. Okay, so on the left of this picture here, you have the ADC. Okay, it has a very high data rate output, but it's only 1 bit. And then you go into basically what is a series of low-pass filters. Okay, and this removes all the up and down part and just gets at the average value of the signal over time. And then you don't need that high data rate. And these are digital filters, by the way. You don't need that high data rate that you get out of here. What you need is more resolution. So you filter that, you get an answer that is much more accurate, and now all you do is just reduce the data rate because you have too much. So there's a whole lot of technology that goes into this, and it's really intriguing and difficult. One thing that makes this really valuable is the fact that the noise, all the noise of that switching back and forth, all right, you want to filter that out, right? And so what you could do is just put the digital filter on it, but by changing, let's see if I can make it, by changing the integrator here and making this more complex, okay, it's not just an integrator, okay, it's a multi-pole and 0 filter, okay. You can actually change the shape of that noise, all right, the switching noise. Now you can push it to a higher frequency, which basically says that you're making this average, okay, that you're comparing, you're putting more emphasis on the low frequencies, okay, and that's going to be more accurate. And the high frequencies are not going to be as accurate. So you've kind of pushed the noise to the end of the spectrum. And I can't really do justice to the topic right now, probably ever, but you can see that the noise is shaped, okay? The noise is not flat. All that switching noise that came from using 1 bit is actually shaped so it's all out here at the higher frequencies. And low frequencies are fairly free of noise. So that gives you a lot of extra resolution. And it's an extremely powerful concept in modern signal processing, in modern converters, in all kinds of things. The idea of shaping the noise, you know, and this is different than the thermal noise we were talking about before. Thermal noise, you're kind of stuck with that shape most of the time. This is the switching noise. This is what we call the quantization noise, and it's a very, very powerful thing. I apologize for not doing a more thorough job, but we don't have time for a thorough job on that. It's a very interesting topic. Okay, so here it is in action. This is 32 bits. I think this is also an audio device. It is used for audio, instrumentation, chromatography, seismology, which are extremely low frequency, very small signals. So it's a very powerful A to D type, but it's best for continuous signals, okay, like some sort of waveform. Not as good for the case where you just want to take a measurement. You know, like you want to get onto the weigh scale you just want to take a measurement. You don't have a continuous signal you want to digitize. You just want to take a measurement. This is not the right architecture. But for everything else, it is. All right, so very quickly, to kind of compare what we had for the DACs, okay, here's a chart that shows the same thing for ADCs. In the case of the flash, you're making all the outputs of the DAC in advance, and then the comparators are waiting to check those DAC values against the input, all right? Here, all of your DACs are binary weighted in the SAR, and that's very important because it's going to check one bit at a time. MSB, next MSB, so forth down the line. And again, for the sigma delta, it's a time-weighted issue. The information is in the duty cycle. But this one, we haven't talked about yet. And if we still got time, I don't see a clock in place, so I'm just.
46 minutes into your time. 5 minutes to wrap.
Good. Nobody wants lunch anyway, so. Okay, so let me just show you two really intriguing ways that people have thought up to increase the speed of these converters, because speed is important. For high frequency signals, you have to sample them more often to get all the detail. So there are two, pipelining and interleaving. So pipelining is kind of like an assembly line, right, where the work moves, each station, the person does part of the job, and then it moves to the next one and so forth. So you pipeline the operation. The world's fastest assembly line puts out a car, I think it's every 46 seconds, all right? So now, you cannot just build a car in 46 seconds, obviously, right? But this factory, if you look at the output, cars are coming out every 46 seconds, right? And that's because of the pipeline, right? And so that speeds up things incredibly. But, there's a limit to that. If the cars are coming out every 46 seconds, that means that every single one of the sections, every single workstation or whatever workplace, each station has to work in 46 seconds, right? Because if he doesn't get his work done in 46 seconds, then it's going to pile up, right? So everybody's got to be working at 46 seconds. And, there's a limit to how far you can push that, right? I mean, you couldn't say, well, okay, let's do 30 seconds, right? I mean, there's limits to this. So the same is true with ADDs. So another way you could do it is kind of like the pizza oven, right? The pizza oven, you could get a pizza out every minute, right? But that means even if the pizza takes 10, 20 minutes to cook, right, you could get a pizza out every minute, because you have a lot of them cooking at the same time. You have a lot working in parallel, right? You put one in, take one out, put one in somewhere else, So this is what we call interleaving. And the reason we call that will be a little bit clearer further on here. But first of all, the pipeline, and to introduce that to you, because this is my favorite, to introduce that to you, I just want to start with a little background. There is another kind of ADD called subranging, and what they do is it's like the two-stage DAC, right? But it's used for A to Ds. So you determine first of all, which range is it in, and then you move the second stage, and you use that to get the fine detail. So you have a coarse and fine thing going on, and that can be done with something like this, right? So here's the input comes in here, and one of the things you do is you take a flash here, which is say 4 bits, right? And then you convert that. So that's kind of a coarse approximation of what the input is, 4 bits, and then you convert it to analog form and subtract it from the input, right? And then you say, okay, well, how far off were we, right? And the fine converter will tell you that. So it's kind of a two-step, right? You make a general guess with the first flash converter, where it's not a guess. I mean, it's a measurement, but it's a very coarse measurement. And that goes to the DAC. You subtract off that part and say how much is left. And how much is left is known as the residue. So this is a picture showing, old oscilloscopes used to be round, all right, the screens. So that's why it looks round. But here's, so you're putting in a ramp here, and you can see at the output of the DAC, each time the flash goes up another code, the DAC jumps up, and your residue, what's left over, is over here. Okay, now this button's only for my amusement. So anyway, the second flash digitizes that residue, and then the numerical values from the first flash and the second flash are added together to give you the overall output. Okay, so that's a sub-ranging or two-stage kind of A to D. Well, to make it a pipeline, we're going to add two things. Okay, first of all, we're going to add this SH block is sample and hold. It could be track and hold, it's sometimes called. That's what's going to allow you to do the pipelining, all right? Because it's going to take a sample of the residue and hold it for the second stage to use, right? So while the second stage is working, the first stage goes to the next input, right? It's like the assembly line, right? And the sample and hold grabs the signal from the first stage, holds it for the second stage, and the first stage goes on and does the next one. So that's one thing. But the other thing we do that's important here is that we add some gain. And that's because the residue is kind of small, right? And that can actually limit how far you could go with this, how many bits of resolution you can get. Because every time you do a flash and you do an approximation, you remove that, the signal gets smaller and smaller and smaller, right? You can't work with that, so you put some gain in there so that basically the signal stays the same size as it moves down this pipeline. And this pipeline could be 12 stages, you know? I mean, I just show 2 here for simplicity, but it could be like 12. Okay, so this is how it works. So just to compare, you know, the subranging, you know, you don't have any gain, right? And so that usually limits you to 2 stages and fairly low resolution, about 10 bits. But with the pipeline, you could have many more stages. It usually doesn't go beyond 12, but you know, you can have a lot. There's various trade-offs, and you can get to much higher resolution with that. Okay, so, but the real magic, I mean, we used to make, you know, A to Ds that look like this. The real magic happened by somebody had a breakthrough about how to do this. And you see that in this next, there's one circuit that can do everything in that dashed block, right? The only thing outside of there is kind of the flash and the digital stuff out here. The DAC, the summation, the gain, and the sample and hold can all be done by one circuit. And that is our friend, that switch capacitor DAC. Okay, this can all be done, because remember, when we're doing the SAR, you can sample the input in there, okay? And then once you open the switches, that sample is trapped in there, so it's a sample and hold, okay? So that's where the sample and hold function is coming from, and then the DAC function is pretty obvious, but also, by making the capacitor up here, by making that small, you get gain, right? So the signals from this, you know, by making the feedback capacitor small relative to the inputs, you get gain, and there's a certain amount of gain you want, and this happens to give you exactly the gain you need. Gives you that. So all of that is kind of, combined into one function. And this particular slide just shows what we call the sampling phase, all right, where you're connecting all the caps to the input, but the feedback is shorted, okay? So you're gonna trap the charge on that summing junction there when that switch opens. And then the next phase, you're gonna switch, I guess what I need to go is this phase. Okay, now you're gonna switch the feedback cap into place, and now you're gonna use the switches to take the data from the flash. Now, one of the interesting things is the flash information is not in binary form. Remember, it was just like there's, for each voltage tap, there's another comparator. So that, the data that comes off of that flash is not in binary form. But that's fine, because we can use that, each comparator will drive one of these switches, and we'll make all of those capacitors the same value. So those capacitors are all the same value, and depending on how many comparators are positive, determines how many of those switches will be connected to the reference as opposed to ground. And so you can see that the signal that the DAC creates is directly driven by how many of the comparators were positive. So this one block, okay, just the one op amp, does all of those functions, and it is very, very fast. Yeah, so this special thing, this switch cap DAC, often referred to as MDAC for multiplying DAC, is an incredibly creative breakthrough. And it is still the standard for the highest kind of commercial A to Ds, I think. So this is a 12-bit product operating at 10 gigasamples per second, has a bandwidth of 6.5 gigahertz. Very popular with the cellular base station people. So this is a very high performance part. All right. This is just to illustrate. One of the problems that you have is what to do with the data, right? Because you are one of these A to Ds. I forget what the number is, but one of these A to Ds generates as much data as YouTube takes in, over the course of a day. It's just phenomenal. I mean, you're getting this data out at 10 gigasamples per second. What are you going to do with it, right? And if you're making a standalone product, just one chip that has an A to D on it, like this, you're going to have to use some pretty extreme data communication, right? And so this has what we call SerDes or serial parallel interfaces. So it has 16 serial lanes operating at 16 gigasamples per second. So just the inter-chip communication for something like this is a science in itself. Lots to be done there. Okay, so finally, and we are nearing the end, the interleaved thing looks like this, okay? And now you can see why I was calling it interleaved, because you're switching the input to one of these ADCs, and you're taking the output from another. And this idea has been around for a long time. It's kind of like a, rotating, it's like the pizza oven. You put one in and then you take another one out. This idea has been around for a while, but it wasn't practical. First of all, because, the A to Ds were too big, and so to duplicate it 4 times or 256 times, which some people do, is just not practical. The other thing is that this kind of architecture, the ADCs have to be very, very well matched, right? Because if they're not matched, then even when you just put in DC, the signal isn't changing, the output is changing because each one has a different gain or a different offset. So you basically have to calibrate these things, right? And that wasn't possible until recently with having enough digital power on board. And here's a little picture of what it looks like. If you just put this thing together and don't have any calibration, you see you can get all those noise spurs, and so it looks pretty ugly. If you add calibration, boom, all right? So you can still see that you get some of the, whoops. You still have some distortion, but it's the normal large signal distortion. All those defects from the mismatches in the comparators have gone away. And there's even another trick here, which I love, and it just kind of shows the creativity of this. Instead of doing them in sequence, you put the input in here, put the input in there, then you take the output here, instead of doing them in sequence, you randomize it, right? You put the input in here, then down there, and you jump back and forth around all those converters, right? Now the mismatch defects are themselves randomized, right? So instead of looking like a tone in your spectrum, which is really annoying, okay, because it looks like a signal. Instead of looking like a tone, it looks like random noise, right? And so all of that goes away. Now, there is a price for that. I mean, you have to have extra equipment to be able to do that, extra hardware, but it's extremely effective, and it makes a wonderful commercial product, which I actually worked on. But it gives you an idea of the kind of creativity that people have when they're working with this stuff. All right, so let's wrap up. There isn't a lot of summary here, but the fundamental principles I want to leave you with is that every DAC must have a reference, and every ADC must have a DAC. Okay, so those are two things to keep in mind, and to look for when you're looking at circuits like this. And again, I wanted to say, that there's just an amazing amount of interesting stuff that goes on with converters, and I think I can recommend it as something to pursue, something to study. So I hope to see you in line for converter work in the future. One final thing, a lot of the stuff I took was from this thing called the Data Converter Handbook. Again, it's not the only, there's lots of references on this, but this one you can download for free. And it has a lot of standard industry kind of references and definitions. So that's it. Now you know all about converters.